Hey, guess what time it is, class? It's science time. Now take out your notes and let's get learning. Hello, class. I hope all of you are doing well. So today we're going to be getting into determining chemical formulas, and this is going to be broken down into two sections. The first section is going to be dealing with what's called the simplest formulas or the empirical formulas. The second section is going to be dealing with a section called molecular formulas. They both work together, and so you first have to understand the simplest or the empirical formulas before we start getting into the molecular formulas. And this is actually doing what we had just done recently when we were finding out the percent composition, and where we took a formula and find out what is the percent by mass of each one of the elements within the compound. This is doing the same thing, but in reverse. Or a lot of times you're going to have a percentage, and how do you work it back so you can find out what is the formula for the compound. Now, the first thing we're looking at here is called the simplest or the empirical formulas, and this is kind of the simplified formula for the compound. So the definition of this is it consists of the symbols for the elements combined with subscripts showing the smallest whole number ratios of the atoms. And the key thing about this is that it is the smallest whole number ratios. Okay, that's going to be a little bit different when we start getting into the molecular formulas. So let's move on. Now what we're looking at is how this data is being analyzed. And there are several different types of devices that's often used in both chemistry and physics to analyze different types of substances. If you ever watch TV shows like CSI or some of this crime type of TV shows, you know, a lot of times they'll take a sample, they'll put it inside of a machine, they push a few buttons, and in a matter of minutes they end up getting the results. Those machines do exist on the most part. Just the amount of time for them to actually work is a lot longer. And just for the sake for the amount of time on a TV show, they have it down where it occurs within a matter of moments, when in reality it may take many hours, sometimes many days, or sometimes even weeks for them to get all the results. So just for the sake of time for a TV show, a lot of times they speed these things up. But the type of information that they will get will be something that looks like this. And they will have several different types of equipment analyzing chemicals in several different ways. And they will not just necessarily just take the readings from one type of machine here, but they will do several different variations of a test on the same sample, and they will help support one another with the results. So they don't just look at one data here, but they use several bits of data, and as long as they're all in agreement with each other here, then they can say with high degree of certainty it is of this substance. So the one way of analyzing it is that, like in this case right here, you have these three prominent spikes, and the amount of spike is in relation to the amount of material that you have, or the percentage of the material that you have. So in other words, if you were to take something like, say this smaller spike versus this larger one here, is that if you look, what is the percentage height of this one in ratio to the height of this one? So if these are two different types of substances, they can use that as a means of determining what is the proportions of each one of the substances within the compound. So basically, the larger the spike, the more of that material that you have. And here's another variation where each one of the spikes is a different part of a compound, and this is most likely some sort of organic type of material. And so with each one of those spikes here, each substance has its own unique, might as well say its own unique type of fingerprint. And you can identify what the material is based upon the amount of the spikes and also the locations of the spikes in relation to the other ones. Here's another type of device. This is a mass spectrometer, and what they do is they take a sample inside of here, they heat up to a very high temperature to the point where the material begins to not only turn into gas, but also begins to ionize. In other words, it is basically almost like a plasma. And they charge up the particles. They put it into an accelerator, which basically it compresses the gas into a very fine stream of particles, and it's moving at a very high rate of speed, and then it goes through a 90-degree bend. And this magnetic field is something that will cause anything that has a charge to it to be deflected. And if you remember towards the beginning of the school year when we're going over like the discovery of the electron, and there was a device called a cathode ray tube, which eventually gave rise to radar and television screens. And if you remember showing the videos where you put a magnet up to a TV set, the old style TV sets, it will cause the image to become distorted. Basically, that's what this device is doing here. Just a reminder, please don't do that to any type of TV screen or monitor. But as the particles are moving around this bend here, you can control the amount of magnetic field which is taking place here. The lighter materials will go in, and if they're too light, they'll smash on the inside of the turn. If there's something that's too heavy, they'll kind of sweep out a little bit further and hit the outer part of the bend. And then if it has a certain type of mass, it's able to make that turn and hit the detector on the opposite end of it here. So you can tune this magnetic field. You can increase or decrease the magnetic field, and the heavier materials will always go to the outside. The lighter materials will always go to the inside, and whatever you have it tuned to was the only thing which is able to go through here. So if you tune it to have a very specific type of mass, it's only detecting that material here. And again, the way they end up seeing this here is a series of spikes. And so each material will have its own unique spike for that strength of magnetic field. This is called a mass spectrometer. If you ever end up taking Chem 2, this is one thing that we end up using as well. Not quite as fancy as this one here, but it is something which is very similar to that. But you can also identify material based upon the colors of light that's being produced here. And so in this case, if you heat a material, and a lot of times it's passed through a flame or something that's heated up to a very high temperature, the material will produce a certain bands of light. Now, as you can see here, I'm not exactly sure what this material is, but you'll get a rainbow, but you will not get the full rainbow. In other words, you don't get the transition. It goes from red to violet. Instead, you will have these bright spots, and then you'll have these dark bands. And again, this is kind of like a fingerprint for that type of material. You can identify what the material is based upon these bands of colored light. This is also part of the reason why during the 4th of July, you will have different fireworks will have different colors, and that is based upon the types of, in this case here, the type of metallic salts. For example, sodium will a lot of times will produce kind of an orangish yellow color. Copper will produce a green. Potassium will produce more of a kind of a purplish color. If you want red, a lot of times they use strontium. And that has to do with the types of lights, bands of light that this thing's producing here. One thing I would advise you to do when 4th of July starts coming around, if you can ever find something that's called fireworks glasses. They kind of look like this 3D style glasses, but they have a clear plastic film. And if you take those and wear those during the 4th of July celebrations as you're watching the fireworks, you'll see them the light being broken down into different types of colors, rainbows. What you're technically seeing is this right here. And you can actually use those to determine what is the chemical makeup of that material based upon those bands of light. And this is another type of device. It's called an NMR. It stands for nuclear magnetic resonance. It's typically used for H1 and C13. Those are isotopes. So H1 is a hydrogen 1. We only have 1 proton and 1 electron. You also have C13, where you have 6 protons and 7 neutrons. And basically this is like an MRI machine. It produces a very strong, powerful magnetic field. A lot of times on the floor, they'll have a line drawn on the floor that you do not cross that line if you have any type of metals or electronic or pacemakers or anything of that sort here, because it can damage those type of things here. So this is basically a very strong magnetic field, but instead of putting a person inside of it, you put a substance. A lot of times it's a hydrocarbon material, some sort of organic material on the inside of this. It has liquid nitrogen and liquid helium. And one thing you have to understand with liquid helium, it gets about 4 degrees Kelvin. In other words, about 4 degrees Celsius higher than absolute zero. So there's extremely cold temperatures. But it uses a very strong magnetic field, and it also uses a radio frequency, and it causes the hydrogen 1 and C13 atoms to do these flips. And it then also starts producing these spikes. And from that, you can determine what type of carbons do you have and what type of bonds do you have occurring between the carbon atoms. So basically, we use all this information, and based upon this information, we can then figure out what is this compound, and then even get to the point where something like this is also figuring out what atoms are attached to what atoms. Now, the process that you go through, this is for the calculations. So from the percent composition, you find the composition by mass by assuming that there are 100 grams of the compound. Now, if you remember when we were doing finding the percent composition, you took the formula and then you find the percentage, but that was the percent by mass. And I made sure that when I was saying that, that is determined by the mass of the material. So now we're going to be taking this information and we're basically reversing it. So if you have 25%, that means you would have assumed that you have 100 grams of it. That would mean you would have 25 grams of that material. Or the other thing you could also have is you may not have a percentage, but you may just have the mass of the material. In other words, you may have so many grams of this one element and so many grams of another element, and they both react together. Later on, I will be showing you a lab that actually works more off of this. The next step is you find the composition in moles of each element. In other words, you take the grams and you convert it to moles. This is where you put 1 mole over the formula weight of that element. So you want to take the percent, convert to grams to moles. Number 3, you set up the moles of each element as ratios and divide by the smallest mole. So initially, when you find the moles, that's kind of your formula. But a lot of times the numbers are some kind of unusual looking numbers, but to make the numbers into whole numbers, you divide by the smallest one. And then number 4, you're going to round the numbers to whole numbers if necessary. In other words, when you're dividing by the smallest one here, because of rounding, you may not get a perfectly whole number. In other words, you might get something like 0.998, so you round it up to 1. Or you may get 4.003, so you just round it to 4. So look at see if it's close to being a whole number. Number 5, if the moles numbers are some number 0.5, n 0.5, in other words, it could be 0.5, 1.5, 2.5, you multiply all the moles by 2. If the mole numbers are n 0.333 or n 0.667, then you multiply all the moles by 3. In other words, it could be 0.333, 1.333, 2.333, same thing with this right here. So this could be any number for n. But if it's any number 0.3 or 0.6 repeating or close to it, you multiply everything by 3. This last one, it tends to be very rare, but if you have some number 0.25, you multiply everything by 4. Now if you look, what's happening with each one of those is that if you have some number 0.5, you multiply by 2, it turns it into a whole number. And if you have like a 0.5 times 2, that's 1. If you have 1.5 times 2, that becomes 3. Same thing with this. If you have some number 0.3 or some number 0.6 repeating here, if you multiply by 3, it turns it into a whole number or nearly into a whole number. And the same thing with this. If you have any number 0.25, when you multiply it by 4, it turns it into a whole number. All right, before we get started, the first thing I want you to do is to create a flow chart. And so get yourself a clean sheet of paper And I want you to write down the following information. So you start off with a percent, and then a percent to grams. And this is where you assume you have 100 grams of material here. So if you, for example, if you have 25%, that simply just becomes 25 grams. So you just convert the percentage symbol into a gram. And then you want to go from grams to moles. And in order to go from grams to moles, this is where you're either going to be using the periodic table or the formula weight. The same thing that you've already done before and doing some of those conversions. Then, once you have the moles, you're going to set them up as a ratio. Once you have them set up as a ratio, next step is to divide by the smallest mole. And what's going to happen here is you're going to be taking the answers you got from here and turn them into something that's a little bit more of a whole number. Then, at that point, one of several different things are going to happen. So after you divide by the smallest mole, you're either going to end up with a whole number. So I'm just going to use a lowercase n just to represent a whole number. Or the other possibility is you might have some number 0.5. And again, it might be something like 0.499 or 2.501. So basically, some number 0.5. If that's the case, then you multiply everything by 2. Or you might have some number 0.3 repeating, or some number 0.6 repeating. Then you multiply everything by 3. And this tends to be very rare, but the other option is it could be some number 0.25. If that's the case, you multiply everything by 4. So we're going to be using this flowchart quite a bit in all the problems here. And then when we start getting to molecular formulas, we're going to add just a little bit more to this. So go ahead, make this flowchart, put it someplace where you're able to refer to it, and let's get started on some of the example problems. Now, if you remember from a few days ago, when we first started going over percent composition, we did a problem like this. And you had, when you're finding out the percent composition, and for example, if you're finding out the percentage of an element, you would take the mass of the element over the formula weight of the compound multiplied by 100. Or basically, a percent composition is part over the whole thing times 100. When you multiply by 100, you're basing it out of 100. So in this case, since all these masses are in grams, when you multiply by 100, you're making it based upon 100 grams. So one of the examples we had done from the very early beginning here was the BIP3. And this is like your binder clips, your index cards, and your 3 paper clips. So this was kind of like our molecule. And since we weighed out a dozen binder clips, a dozen index cards, a dozen paper clips, we're able to find out from this BIP3 what was the mass of the whole thing. And to find out the percentage, since these were our parts, and this is the weight of the whole thing, we were able to find out what is a percentage of each one of the individual parts that makes up this supposed molecule. So, for example, for the binder clips, we had 34.41 grams. The weight of the whole BIP3 is 112.28 grams for every 1 dozen. So we took the mass of the binder clips, or the mass of the whole thing, and we found out of the weight of this whole BIP3, a little over 30% of it were binder clips. And then we did the same thing with the index cards. Took the mass over the whole thing, multiplied by 100. We have almost 27.5% index cards. And the same thing with the paper clips. There were 3 paper clips on every binder clip and index card. We get the mass of the paper clips, mass of the whole thing. So we have this down here, and almost 42% of it were made up of paper clips. And if you add up all these results together, we end up getting something close to 100%. So this means that if I were to weigh out 100 grams of this BIP3, I should have 30.647 grams of it be binder clips, 27.485 grams of it should be index cards, and about 41.869 grams of it should be paper clips. So what we're going to be doing now is basically taking this information and working backwards to find this. So we're going from percent to formula, because last time we went from formula to percent. So now we're going to be working backwards. So this is kind of like in forensic science or analytical sciences. They will take an unknown sample, they'll analyze it, they'll find out what are the percentages of that substance. Based upon those percentages, they need to be able to work backwards and find out what this is. So we're pretending like we don't know what this is. But we analyzed the material and we found this. So based on this, we need to find out this. So we're pretending as though we don't know it's BIP3. So let me show you how to go about doing this. So what I'm going to do is copy down these values here. So for binder clips, I have 30.647% of binder clips, 27.485% of index cards, and 41.869% of paper clips. Okay. Now I also will eventually need to get what is the weight of a dozen of these. This is kind of like my periodic table. So going back to the flowchart, going back to this, I have a percent. So this is basically the sequence that we're going to be going through here. For some of the problems, we're going to be starting off with a percent. Sometimes we won't have a percentage, we'll only have grams. And it doesn't always have to add up to be 100 grams either. As long as it is the mass of the material that's making up the compound. So if it's a percentage, it should have to be 100. It can also start with grams where it does not have to start at 100. Sometimes it can be a lot less than 100 grams, sometimes it can be a lot more than 100 grams. In some cases, you might even just have how many moles, or basically the kind of like the formula of it. So typically, we're going to be starting in one of these three locations here. But the sequence is always going from the left to the right. So since we have the percentage here, first step is assume you have 100 grams. So whatever the percentages are, make those into grams. So if I have 30.647% of binder clips, that means I'm going to have 30.647 grams of binder clips. Same thing for the index cards. 27.485% becomes 27.485 grams of index cards. And for the paper clips, I will have 41.869 grams of paper clips. So all we did was convert percent to grams. You assume you have 100 grams of it, so therefore if I have 100 grams of this material, this will be how many grams of each one of the materials I would have. Next step is to go from grams to moles. And a lot of times you would be using the periodic table. Now, since binder clips are not on the periodic table, we're going to use back to this, or even, let's see here, or even back to this. Like for binder clips, okay, 1 dozen was 34.41 grams. So I already have the unit grams. But in this case, I want to go, a lot of times you want to go from grams to moles, but what we're using here, the equivalent of a mole is a dozen. So I want to go from grams to dozen. So since 1 dozen is equal to 34.41 grams, this becomes my conversion unit here. So I'm going to open up a set of parentheses, and I want grams to cancel out. So technically, this whole thing is over 1. So in order for grams to cancel out, I need grams on the bottom, which means I'm going to put 34.41 grams on the bottom and 1 dozen on top. All right, and this way grams will cancel out. For index cards, 1 dozen index cards was 30.86 grams. Same thing. Technically, this whole thing is over 1. Grams is on top. In order for it to cancel out, I need grams on the bottom. So I'm going to put 30.86 grams on the bottom and 1 dozen on top. And for paper clips, I have 15.67 grams for every 1 dozen. So technically this whole thing is over 1. So I need grams on the bottom. So I'm going to put 15.67 grams on the bottom, 1 dozen on top. Okay. So now the grams will cancel out. And what the unit we're going to have left over is dozen. It's the same thing we have up here. Ultimately, we'll end up with the unit moles when we're done with the elements. So let's work this out. So I'm taking 30.647. Technically, you're divided by the bottom, you're multiplied by the top. So I'm taking 30.647 divided by 1 times 1 divided by 34.41. Or a little bit faster here, just take 30.647 divided by 34.41. All right, so I'm taking 30.647 divided by 34.41. Multiply the top, divide the bottom. So I have 0.8906. Typically, if you take about 4 places past the first non-zero digit after the decimal point, you should be okay. And the unit that would be dozen. And that is of binder clips. So write down the number, what unit, and then what is the substance. Then we're going to do the same thing with the next one. At 27.485 divided by 30.86. And I get 0.8906 dozen of index cards. Now, if you round it too much, like 0.9, a lot of times you might end up losing some information here. So again, take it about minimum of 3, but typically take about 4 places past the first non-zero digit. And then for the last one, we have 41.869. I want to divide it by 15.67. And that comes out to be 2.6719 dozen of paper clips. So technically, that is our formula. And that would be where the formula would be binder clips 0.8906, index cards 0.8906, 6, paper clips 2.6719. Thing is, that doesn't make a whole lot of sense. And this will be fine if you're working with a large group, like dozens or moles or something like that. But when you're dealing with individual particles, you do not have a part of a binder clip. I suppose you could, but we're trying to treat this like atoms here, where you cannot have a fraction of an atom. Same thing with this. We're assuming that we cannot have a fraction of a binder clip, or a fraction of an index card, or a fraction of a paper clip. So to alleviate that, that's where we go to the next part here. So we figured out the moles, or in this case here, we figured out how many dozens. Let me put this way so you can see it here. So we figured out the number of dozens, which is kind of like figuring out the number of moles. So the next step is find the ratio. So we're going to set this to ratio. And the way, so I'm just going to draw a line through this. We really don't need this part right here. So for the ratio, we have 0.8906 dozen binder clips is in ratio to 0.8906 dozen index cards, which is in ratio to 2.6719 dozen paper clips. So you set them up as a ratio. Then the next part is you want to divide by the smallest mole. In this case, we're going to divide by the smallest dozen. So you look at, in this case, these three right here. You find the one which is the smallest one. When we have two of them, they have the same number. So it really doesn't matter which one. So 0.8906. So you're going to divide all three of these by the same number. So in this case, if I do that, I end up with 1 dozen. I'm going to end up with 1 dozen binder clips. If I divide these two, I'm going to have 1 dozen index cards. And then this last part, I have 2.6719 divided by 0.8906. And if you notice the number here, 3.000112284. Basically, we have 3. Now the reason why we didn't get exact here is because we also rounded these numbers here. And also very early on, when we're getting these values over here, these are also rounded. So all those little rounding introduce a little bit of errors to the values here. But basically, as you can see here, we have 3 dozen paper clips. So therefore, well, as you can see, all 3 of these are whole numbers. So that goes to this. So the fact that all the numbers are basically whole numbers, we don't have to do anything after that. If just one of the numbers was a, like for example, was a 0.5, then you multiply everything by 2. Okay, but in this case, all 3 of the numbers were whole numbers. So we don't do anything else after that. So this becomes your formula. And what does this mean? This means you have 1 dozen binder clips, so you can just write down B. 1 dozen index cards, I. 3 dozen paper clips, P3. BIP3. And that is what we had to start off with. Is that last time we had 1 dozen BIP3, and you went through this process to find out the percentage of each one of the substances. What we've just done is we took these percentages and we worked through to find out what is the formula for it. And again, in stuff like in forensics and analytical chemistry, this is something which is done quite a bit. Is they'll analyze a material, they'll find out what are the percentages of each one of the substances within it, and then they'll go through and find out, basically go through this process here, find out how many moles you have, and then ultimately figure out what is the formula for the compound. So what we're going to be doing now is exactly the same thing. The only thing we're going to be changing here is we will not be working with the unit dozen. We're going to be working with a much larger unit of the mole. But it's exactly the same thing that we just did with this. All right, let's go ahead and move on. All right, so let's go through some examples And what I would recommend doing is watch how I go about working these things out. And after about the first one or two of these, then pause the video, work it out, and then play the video and see how close did you get to that value. So the first one, a compound is found to contain 63.52% iron and 36.48% sulfur. Find its simplest formula. For number one, we have 63.52% iron and 36.48% sulfur. Okay, so now on the flow chart, since we're starting with percentages, the first step is assume you have 100 grams. So all we're doing is just changing the signs from percentage to grams. You know, if you add these two values together here, you should get 100% or something very close to being 100%. So that means we would have 63.52 grams of iron and 36.48 grams of sulfur. So now the next step is convert the grams to moles. And this is where you're going to be using the periodic table. Since we're dealing with elements, you need to look at the periodic table to get this information. So if you look in the periodic table, iron is 55.847 grams for every 1 mole. So technically, this whole thing is over 1. Grams is on top. So in order to cancel it out, I need to have grams on the bottom. So I'm going to put 55.847 grams on the bottom and 1 mole on top. This way grams will cancel out. Same thing for sulfur. Since we have 36.48 grams, technically that is all over 1. So grams is on top. I need grams on the bottom. So if you look for sulfur, sulfur is 32.066 grams. So I need to have that value on the bottom so the units will cancel out. So 32.066 grams. And then the unit 1 mole on top, because that's how many grams it is for every 1 mole. So grams will cancel out. So for iron, 63.52. Remember, you multiply the top, you divide the bottom. So 63.52 times 1, which is going to give you the same number, divided by 55.847. And we get a value of 1.1374 moles of iron. And then for sulfur, we want to take 36.48 times 1 divided by 32.066, and we get 1.13, when you round it, it's about 77 moles of sulfur. Again, take it 3, I would recommend even 4 places past the decimal point, or at least past the first non-zero digit after the decimal point. So now we have the moles. So the next step is go from moles, sum up as a ratio. So technically, what we have right now is the answer. This means it's Fe 1.1374, S 1.1377. Now that doesn't make a whole lot of sense. You know, this would be fine if you're dealing with the unit moles, but this should also be able to represent atoms. And you cannot have this fraction of an atom taking place. So what we're going to do now is sum up as a ratio. So we're going to have 1 mole, we're going to have 1.1374 moles of iron is in ratio to 1.1377 moles of sulfur. So if you look at the flow chart, we sum up as a ratio. Now the next step is divide by the smallest mole. So between these two, the smallest one is this one right here. So I'm going to divide both of these by 1.1374. So when I divide these two, I'm going to end up with 1 mole of iron. When I divide these two, basically, if you can notice here, it's going to be slightly over 1 mole here, but basically it's going to be 1 mole of sulfur. So therefore, the formula for this is FeS, 1 iron, 1 sulfur. Or the name for it would be iron 2 sulfide. And the other name for it would be ferrous sulfide. Now, it won't show you the charges of this here, but just iron can have multiple charges to it. A lot of times it's +2, +3. So you look at sulfur. Sulfur has a -2 charge. Therefore, this iron must have a +2 charge to balance it out. And that's the reason why it's iron 2 sulfide, or ferrous, which is iron with a +2. So this here is your answer. So ferrous sulfide has 63.52% iron and 36.48% sulfur. So in other words, if I were to measure out 100 grams of ferrous sulfide, it would be made up of 63.52 grams of iron and 36.48 grams of sulfur. All right, now let's move on to the next one. Number 2. Find the simplest formula of a compound found to contain 15.772% aluminum, 28.114% sulfur, and 56.114% oxygen. And for number 2, we have 15.772% aluminum. So 15.772% of aluminum. 28.114% of sulfur, and 56.114% of oxygen. So if you look at the flow chart, we have the unit percentages. We need to convert these into grams. So you assume you have 100 grams of this compound. We don't know what it is yet. So if you have 100 grams of this, that would mean that you would have 15.772 grams of it would be aluminum. 28.114 grams of it would be sulfur. And 56.114 grams of it would be oxygen. So the next step is we need to go from grams to moles. So we need to use a periodic table. So open up a set of parentheses. If you look on the periodic table, aluminum is 26.982 grams. Again, this whole thing is over 1. So therefore, I need to have the unit grams on the bottom, because grams is up on top over here. So I'm going to put 26.982 grams on the bottom and 1 mole on top. Same thing for sulfur. Sulfur is 32.066 grams. So all of this is technically over 1. So I need to put 1 mole on top and 32.066 grams on the bottom. And for oxygen, same thing. Oxygen has a formula weight of 15.9994 grams. Probably by now you have that number memorized. All right, so now grams will cancel out. All these grams will cancel out. So if you take 15.772 divided by 26.982, you get a value of 0.5845 moles of aluminum. If you take 28.114 divided by 32.066, you get 0.8768 moles of sulfur. And same thing for oxygen, you would have 3.5073 moles of oxygen. Then the next step is, since we had the unit moles, is we need to go to set them up as a ratio. So we would have 0.5845 moles of aluminum is in ratio to 0.8768 moles of sulfur, which is in ratio to 3.5073 moles of oxygen. All right, so we have the ratio. Next step is divide by the smallest mole. So I'm going to take all of this, and the smallest number here is the 0.5845. So I'm going to divide all three of those by 0.5845. So obviously one of these is always going to be a 1, since you're always dividing by the smallest one. So I'm going to have 1 mole of aluminum. Next one is when you divide these two, it comes out to be about 1.5. Okay, so just kind of show you real quickly. If you take 0.8768 divided by 0.5845, you get just slightly over 1.5. Now this is one of those situations there when you're looking at this, you don't say, well, okay, well, I need to round this number up. What you're looking for are either whole numbers, halves, so in other words, some number 0.5, thirds or 2/3. So in other words, you will see like 0.3, like 333, or 0.666 or 0.667, or quarters. So like some number 0.25. In this case here, this is very close to being 1/2, or it's almost essentially 1/2. And then when you divide 3.5073 divided by 0.5845, you end up getting 6 moles. Now, we have 1 mole of aluminum, 1.5 moles of sulfur, 6 moles of oxygen. So the fact that one of these has a 0.5 to it. Next step is you multiply everything by 2. Now, if you remember back when we were balancing chemical reactions, and especially for some of the combustion reactions, this is kind of similar to the coefficient numbers. It is that if you remember the ones where sometimes it wouldn't balance out, but it would balance out if one of them could be a half. A lot of times it was oxygen. And so if you could make that into a half, therefore if you multiply everything by 2, you would end up getting where everything would be in correct proportions here. And I remember telling you guys is that try to remember when you're balancing out the reactions, and if you could balance it out with a 0.5, then you would have to multiply everything by 2 in order to make it into a whole number. And I said later on, you're going to be seeing something very similar to this. That's the situation that I'm talking about previously. So you don't just multiply this by 2, because it is a 1 to 1.5 to 6 ratio. So you have to maintain the same ratio. So that means we need to multiply everything here by 2. Now, if this was a unit moles, or even like the unit dozens, this would work. Because you can have, for example, like 1.5 dozen sulfurs. Okay, so that would mean you would have 18 atoms of sulfur. Or, 1 mole, or saying like 1 dozen aluminums, or 6 dozen oxygens. You can have a fraction of a dozen, or a fraction of a quantity. What does not work is when you're dealing with individual atoms, because these proportions should also apply to atoms as well. You cannot have half of an atom. So you multiply everything here by 2, which means you're going to have 2 moles of aluminum. 1.5 times 2 is going to be 3 moles of sulfur. And 2 times 6 is going to be 12 moles of oxygen. So, therefore, our formula is Al2S3O12. Now, do you recognize that formula? Because that's actually one of the compounds you've written out when you were writing out compounds. You may not be able to recognize it because with the sulfur and oxygen, you didn't come across any polyatomic ions that contain this many sulfurs and this many oxygens. So let me show you something here. If I cover up the aluminum, because aluminum has a positive 3 charge, but here we have something that maybe you might be able to recognize. You have the numbers 3 and 12. These two numbers can be reduced down. Now, not all three of these numbers can be reduced down. Just these two can be. And if you look at this, both of these are divisible by 3. So if I divide both of these by 3, I end up with SO4. And then I also have my aluminum, Al2. Now, because these can be reduced down, I still need to have 3 sulfurs and 12 oxygens. So what we're going to have, let's close this up in parentheses, 3. You recognize it now? So aluminum has a positive 3 charge. SO4 is your sulfate, which has a negative 2 charge. So you have 2 negative 3, so that gives you an overall negative 6. 2 times positive 3 gives you a positive 6. So positive 6, negative 6, the whole thing is neutral. So this is aluminum sulfate. Now the one thing when you're doing the empirical formulas, it cannot show you parentheses. It will show you like the total number of each one of the elements, but you cannot see like how many clusters of sulfates we have. In other words, it cannot show you that you have 3 clusters of sulfates attached to these 2 aluminums. It will just simply tell you you have 3 sulfurs and 12 oxygens. But this is actually this. So whether you wrote this down or wrote this down, either one's fine. But if I'm asking what is the name for the compound, you might have to look at this and then figure out this part of it here. Okay, so let's move on. Number 3, analysis shows a compound contains 26.56% potassium, 35.41% chromium, 38.03% oxygen. Find the simplest formula of this compound. All right, so for number 3, we have 26.56% potassiums, 35.41% of chromium, and 38.03% of oxygen. So the first step is we need to go from percent to grams. So that means you would have 26.56 grams of potassium, 35.41 grams of chromium, and 38.03 grams of oxygen. And then we need to go from grams to moles, so we need to use a periodic table. So you have to look at the periodic table, and potassium has a formula weight of 39.0983 grams. So again, this whole thing is over 1, so I need grams on the bottom. 1 mole will go on top, so 39.0983. For chromium is 51.996 grams for every 1 mole. So I need to put 1 mole on top, and 51.996 grams. For oxygen, everyone together, 15.9994 grams for every 1 mole. So grams will cancel out. And so when you divide it out, for potassium, you get 0.6793 moles of potassium. For chromium, you get 0.681, basically 0 moles of chromium. And for oxygen, it's 2.377, basically it kind of rounds to 0 moles of oxygen. So we have the moles. Now we need to set up a ratio. So we're going to have 0.6793 moles of potassium is in ratio to 0.6810 moles of chromium, which is in ratio to 2.3770 moles of oxygen. Then we're going to divide by the smallest mole. So looking at all three of these numbers here, the smallest one will be for the potassium, which is 0.6793. So that means we're going to have 1 mole of potassium. We're going to have, if you know, sometimes you can just tell, but just by looking at it here, basically 1 mole of chromium. And when you divide these two, initially you get like 3.499. So basically, that is 3.5 moles of oxygen. Now, since we have a number that's some number 0.5, we need to multiply everything by 2. So this whole quantity will need to be multiplied by 2. So that's going to give us 2 moles of potassium, 2 moles of chromium. 3.5 times 2 is 7 moles of oxygen. So that means the formula is 2 potassiums, 2 chromiums, and 7 oxygens. Hopefully you recognize this. This is potassium, which is positive 1. This is dichromate, which has a negative 2 charge. That's the reason why there's 2 potassiums down here. So this is your answer here, which is potassium dichromate. All right. Hopefully you did well on that one. Let's move on to the next one. Number 4. Analysis of a 10.15 gram sample of a compound is known to contain only phosphorus and oxygen. 5.717 grams of oxygen was produced from the breakdown of the sample. What is the simplest formula of this compound? Now, one thing I also want to say here is put a little star by this one. You're going to be seeing this problem a little bit later on again. Now, for number 4, this is one where I want you to remember this one because you're going to see this problem when we start getting into molecular formulas. So we're going to be expanding upon this one a little bit later on. Now, this one's also a little bit different in that you do not have percentages, you only have masses. And it also does not add up to be 100. It does not have to add up to be 100. So this is an example where you have to do a little bit extra work in order to figure out the substance here. So you have a compound that contains phosphorus and oxygen. Now the thing is, you don't know how much phosphorus and how much oxygen. You just know it has phosphorus and oxygen. So I'm just going down PO. So you could possibly put like X and Y here. We just don't know what these two values are. But it just has phosphorus and oxygen, and the mass of the whole thing was 10.15 grams. And then it went through some decomposition, and you measured the amount of oxygen from this reaction here, and the amount of oxygen was 5.717 grams. Now, just by looking at this, in other words, it's phosphorus and oxygen has a total mass of this. You decompose the material, and you've measured the amount of oxygen to be this many grams. So we need to find out, like on this flow chart, when we're going from grams to moles, we need to know how many grams of just phosphorus do we have. So the way we can figure this out is by not dividing, but subtracting this whole thing. So when we subtract it out, the amount of phosphorus comes out to be 4.433 grams. So this part up here, we don't need that anymore, because now we know how many grams of oxygen and how many grams of phosphorus. Now you could do one or two different things here. Since we have this total mass right here, and you know the mass of each one of these parts, we can go back and do part over the whole thing and find out the percentage. That would work. In other words, so if you find out the percentage, you can go from percent to grams, grams to moles, go right down the line here and solve for it. But you don't have to. We already have the unit grams, so we're starting here. So even though it doesn't have to be 100, it does not have to be, because this compound is only made up of phosphorus and oxygen, and if you know the total amount of those two elements, we can just actually start from right here. So it does not have to add up to be 100. So let's go ahead and work this one out. So we have oxygen, and this is how many grams of oxygen. So we need to use a formula weight. So we're going from grams to moles, use a formula weights from the periodic table. So 1 mole of oxygen is 15.9994 grams. And then also, if you look up for phosphorus, phosphorus is 30.974 grams for every 1 mole. So we put 1 mole on top and 30.974 on the bottom. This way grams will cancel out. So 5.717 times 1 divided by 15.9994 comes out to be 0.3573 moles of oxygen. You do the same thing for phosphorus. 4.433 times 1 divided by 30.974 comes out to be 0.1431 moles of phosphorus. So now we have our moles. We need to set them up as a ratio. So I'm going to take 0.3573. I'm sorry. Actually, I want to go the other way here. We'll put phosphorus down. 0.1431 moles of phosphorus is in ratio to 0.3573 moles of oxygen. Now, it would have been okay if I put oxygen first. If you remember back when we first started writing out formulas here, a lot of times you put the positive ion first, and then you put the negative ion last. Positives come first, negatives go last here. But when you're dealing with a binary compound like carbon dioxide and nitrogen monoxide, those type of things here, typically whoever is closest to fluorine goes last. Whoever is furthest away from fluorine goes first. So in this case, if you look at the periodic table, oxygen is closest to fluorine. And so a lot of times oxygen is written last and some of the other elements are written before it. That's the reason why I scribbled this part out. If you didn't, don't worry about it. So I have these two, and then the smallest one is 0.1431. So I want to divide by the smallest mole. So when I divide these two, I'm going to have 1 mole of phosphorus. And then for this part, basically you end up with like 2.49 moles of oxygen, which is basically 2.5 moles of oxygen. So I've got 1 to 2.5 ratio. Again, you cannot have half of an atom. Now you can have a half of a dozen, or in this case even a half of a mole, but this also needs to apply to atoms as well. So you multiply everything here by 2. So therefore you're going to have 2 moles of phosphorus to 5 moles of oxygen, still maintaining that same ratio. So therefore the formula is P2 0.05. The name for this is diphosphorus pentoxide. Remember the binary molecular compounds? The first element, if there's only one, you just say the element name. And if you have two or more, then you use a numerical prefix like di, tri, tetra. The second one, you always use a numerical prefix, and you say its ion name. So you don't call it oxygen, you call it oxide. And then if you have one oxygen, it'd be monoxide. In this case, we have 5. That means 5 is pent. So the first part, you say its element name. Second part, you say its ion name. All right. Now later on, we're going to be coming back to this. So hold on to this paper for later on. Number 5. If 3.5 grams of iron react with 1.5 grams of oxygen, what is the simplest formula of this compound formed? Now, similar to the last one, for number 5, all right, so for number 5, we have 3.5 grams of iron and 1.5 grams of oxygen. Now, unfortunately, I cannot do this demonstration for you guys here, but I believe I did this demonstration here a while back, kind of showing what happens to the mass. So, for example, if you take something like steel wool, which is mostly iron, and you begin to heat it up, or if you take a battery or put it up to a flame, that's where you start seeing the iron begins to melt and begins to oxidize. You have like these little orange things kind of moving around through there, and if you weigh it afterwards, it will end up weighing more than what it was before. And a lot of times, most of the iron is combining with the oxygen, so the mass of it goes up. So you can find out what is the amount of iron to oxygen if you weigh it initially here, and then later on you weigh the whole thing, which would be the total mass of these two. And if you subtract those two, you can find out how many grams of oxygen is attached to it. And if you know number of grams, you can even figure out what is the formula basically for the rust that was formed from that. Now here's another situation where we don't have percentages, and this does not have to be 100. We just have a compound that's made up of this much iron and this many grams of oxygen. So therefore, we can start right here on this flow chart. So we need to go from grams to moles. So we need to use the information from the periodic table. So if you look up the formula weight for iron, which is 55.847 grams for every 1 mole. Technically, this whole thing is over 1. So I need to put the grams on the bottom. And 1 mole on top. Same thing for oxygen. Oxygen is 1 mole, or 15.9994 grams. This way grams will cancel. And for iron, you would have 0.06267 moles of iron. Again, take it about 4 places past the first non-zero digit. And then for oxygen, we have 0.09375 moles of oxygen. So we have the moles. Next step is set up as a ratio. So we're going to take 0.06267 moles of iron is in ratio to 0.09375 moles of oxygen. You want to divide them both by the smallest mole, so which would be the moles of iron. It's not always the first one here, but in this many cases it can be. So we want to end up with 1 mole of iron which is in ratio to 1.5 moles of oxygen. So again, we have a situation where we have some number of 0.5. We must multiply everything by 2. So that means we would have 2 moles of iron to 3 moles of oxygen. So therefore, our formula is Fe2O3. Now, oxygen has a -2 charge. We have 3 of those. That gives you an overall charge of -6. So to make this a +6, and we have 2 irons already, that means this iron has a +3 charge. So therefore, the name for this compound is iron 3 oxide. Or the other name for it is ferric oxide. Common name for it is rust. Technically, this is red rust. So, if you were to take rust and you measure it out 5 grams of it, 3.5 grams of it would be iron, and 1.5 grams of it would be made up of oxygen. So let's move on to the next one. Number 6. A magnesium sulfate hydrate compound is heated and found to contain 48.836% magnesium sulfate and 51.164% water. What is the empirical formula? All right, this next one is going to be kind of unique because we're not dealing with a individual elements. We're now dealing with a compound. So, a magnesium sulfate hydrate compound is heated and found to contain 48.836% magnesium sulfate. So 48.836% magnesium sulfate. And it's also 51.164% water. Now, this is one of those hydrate compounds, which means this magnesium sulfate has some water which is attached to it. We just don't know how many. So, again, if you look at the flow chart, we need to go from percent to grams. So you assume you have 100 grams of it. If you notice here, these percentages add up to be 100, or they should be close to 100. So this will mean we have 48.836 grams of magnesium sulfate. And we would have 51.164 grams of water. Now, we need to go from grams to moles. Now, the problem is, we don't have atoms, we have a compound. We need to find the formula weight for it. So this is where, if you remember from a while back, where we had to take this and break this apart into 1 mole magnesium, 1 mole sulfur, 4 moles of oxygen. Now, just for simplicity, just multiply and add those numbers together here. So in other words, you're going to take oxygen is 15.9994, multiplied by 4. You have 1 sulfur, so add to 32.066, or 32.06, I'm not sure. Magnesium is 24.305. So you're going to add those values together here and find the formula weight for that. So I'm assuming that you've already done that. And so the formula weight, let me put this down here. Magnesium sulfate has a total formula weight of 120.3686 grams per mole. Water has a total mass of 18.0152 grams per mole. These are your formula weights. These two right here. These are your formula weights for those two substances here. So that's what we're going to be using up here. Now this is unit grams per mole, or it's basically saying this many grams is equal to 1 mole. Since grams is already over 1, I need grams on the bottom. So that means I need to put 120.3686 grams on the bottom. 1 mole will go on top. For water, same thing. This is how many grams for every 1 mole. This whole thing is over 1. So that means I need to put 1 mole on top and 18.0152 grams. Grams will cancel out. And when you divide these out, you end up getting 0.4057 moles of magnesium sulfate. I don't have enough room to put down, I can put it down here. Moles of magnesium sulfate. And for water, I have, let's see here, 2.84 moles of water. Okay. So now, since I have the moles, I need to sum up as a ratio. So I'm going to have 0.4057 moles of magnesium sulfate is in ratio to 2.84 moles of water. You want to divide by the smallest mole, which would, in this case, would be the magnesium sulfate. So you're going to end up with 1 mole of magnesium sulfate. And when you do this part of it here, 2.84 divided by 0.4057, you end up with 7 moles. Basically, it should be 7 moles of water, which means the formula is MgSO4. And because this is a hydrated compound, this is where you have the dot, and you're going to have 7 H2O. And that's your formula right there. So the name of the compound is magnesium sulfate hepta, which means 7, hydrate, which means water. Common name for it is Epsom salt. And if you remember, what we just did is the reverse of what we did the other day, where you had the formula of magnesium sulfate, heptahydrate. You broke it apart into 1 mole magnesium, 1 mole sulfur, 4 moles of oxygen. Then you have 7 times 2, you have 14 moles of hydrogen, 7 times 1, 7 moles of oxygen. And then you find the formula weight for magnesium sulfate, 120.3686. Formula weight for water, total weight of the water is 126.1064. And then the total weight of the whole compound is this amount here, a little over 246 grams per mole. And then you find out the percentage of each one here. So what we just did, the percentages we have here, is what you figured out the other day here. So we took the formula, found the percentages. Today we took the percentages and found the formula. And so one thing, if you look at this here, is that the amount of water is quite significant, where it makes up over half the mass of the entire compound. So a little over 50% of it is actually made up of water. Isn't that fascinating? I know, Mr. Souder, that's really cool. Number 7, 60.4 gram of a cupric nitrate hydrate is heated to evaporate the water. After heating, the anhydrous cupric nitrate weighs 46.889 grams. What is the empirical formula of the hydrated compound? Now, a couple things about this is that it's a cupric nitrate hydrate. In other words, you don't know how many waters you have here. So it could be a single water molecule, so it would be a monohydrate. It could be two of them, so it would be dihydrate. So what you're trying to find out is how many waters are here. Anhydrous basically is another word for dehydrated. So the cupric nitrate had water, you heat it up, and now it has no water to it. All right, for number 7, you have 60.4 grams of a cupric nitrate hydrate. So this is similar to the last one with the magnesium sulfate one. So you have 60.4 grams of cupric nitrate, and you made it anhydrous. In other words, you evaporate most of the water, and you end up with 46.889 grams of the anhydrous cupric nitrate. So a couple of things we need to find out first. The cupric nitrate, let's first find the formula weights. Okay, so for cupric nitrate, cupric is Cu, and ic has a positive 2 charge. Nitrate is NO3 negative 1. So therefore, you balance out the charge, you need 2 nitrates. So it's the weight of 1 copper, 2 nitrogens, and 6 oxygens. So when you add up all those masses together, the formula weight for cupric nitrate is 187.5564 grams per mole. For water, the weight of 2 hydrogens and 1 oxygen comes out to be 18.0152 grams per mole. All right, so now let's go ahead and work this part out. So you have 60.4 grams of a cupric nitrate hydrate. And we'll put dot X H2O. We don't know what this is right here. And the mass of the whole thing was 60.4 grams. Then you heated it up, you evaporated the water, because I'm going to get rid of this here. And you have anhydrous cupric nitrate. And when you do that, you had 46.889 grams per mole. So, if the hydrated cupric nitrate had a mass of 60.4, you evaporated the water, and you end up with anhydrous cupric nitrate would have this mass. So by subtracting those two values, you can then find out how many grams of water do you have. So when you subtract them out, you end up with 13.511 grams. Yeah, let me get rid of this here. All right, so we really don't need this information here. So we have this many grams of cupric nitrate, this many grams of water. So let me rewrite this down here. So we have 46.889 grams of cupric nitrate. We have 13.511 grams of water. So we have grams. We need to convert these into moles. So we need to use a formula weight. And so the formula weight for cupric nitrate is 187.5564 grams per mole. Again, this whole thing is over 1, which means I need to have grams on the bottom. So 187.5564 grams will be on the bottom. 1 mole will go on top. Same thing for the water. The grams is on top. I need to have the unit grams on the bottom. So 18.0152 grams and then 1 mole on top. This way grams will cancel. And when he divided out for the cupric nitrate, it came out to be 0.24, basically 99 moles of cupric nitrate. And do the same thing for water. 0.74998 moles of water. Now you might be able to tell just by looking at this as to what's going to be going on. But let's go ahead and set up the next part here. So you have the moles, set up as a ratio. So 0.2499 moles of cupric nitrate is in ratio to 0.74998 moles of water. I'm going to divide both of these by the smallest number, which is 0.2499. If you end up rounding to 0.25 and 0.75, that would also work here too. You would have 1 mole of cupric nitrate is in ratio to 3 moles of water. So therefore, let me move this up here so you can see it a little bit better. So when you divide them out, you get 1 mole of cupric nitrate and 3 moles of water. So the formula becomes CuNO3 2.3H2O. That is your formula here. The name for it, nitrate has a -1. You have 2 of those, therefore that copper has a +2. So this could be called copper 2 nitrate. And the 3 is tri. The word for water is hydrate. Or the other name for it would be cupric nitrate trihydrate. All right, so again, let me kind of go back over this here. So we had this many grams of cupric nitrate hydrate. You had 60.4 grams. You dehydrated it, in other words, you evaporated all the water. And for the cupric nitrates, without any water, was 46.889 grams. By subtracting those two, you'll find out how many grams of it was made up of water. Now, I just messed up on this part over here with the per mole. So you have how many grams of cupric nitrate, how many grams of water. So now, using those grams and using the formula weights, basically using this part right here, so you have to find out the weight of cupric nitrate and the weight of water. So you plug those into here in order to convert the grams into moles. Then we set the moles to ratio. We divide by the smallest mole, and everything came out to be a whole number. And we find out for every 1 copper nitrate, there are 3 water molecules attached to it. So this becomes our formula down here. Hopefully that makes sense. If you have any questions on that stuff, send me an email. I'll do my best to help you out. You have a good day. All right, I'm going to end the video here. And the second part of this is going to be dealing with the molecular formulas. So we're taking what we have just done, and eventually we're going to be expanding upon this into finding basically the true formula of the compound.